Great. Okay. Yeah, so I'm going to be talking about LLM based agents and just give like a survey of the field. So a quick intro about myself. I'm a high schooler going into my 12th grade. I'm from New York City and I've had the opportunity to work as a researcher at NYU. And so we're working on something called LLM-based agents, and I'll explain a little bit more. And anytime throughout the presentation, if you have any questions or anything, feel free to just interrupt. Yeah. Okay. So I'm going to be talking about agents in two primary categories. So the first is human-like agents, or agents that exhibit sort of believable human behavior. And then I'm going to talk about agents for some task completion. So the first will be completing tasks in the web, and then in embodied environments like you see here on the right with Minecraft. And I want to note that the LLM-based agent sort of research area is very broad. And so there's a couple of things that I won't have the time to cover today. But these are things like agents for coding, like autonomous software engineers, also more like high-level society and social network simulations. So because of LLMs, sociologists, economists, they have a whole new wide array of tools, and that's basically like a research area of its own. And then also, I will not be talking about LLM backbones for robotic planning, um, because I'm not really studying robotics. Okay, so there's been a long history of this idea of agents in both computer science research and in philosophy. And an agent just, generally is just some entity that can act autonomously. So there's been many attempts to achieve this in the past with symbolic agents, reactive agents, reinforcement learning based agents, and agents with transfer learning. But large language models provide some new capabilities that these prior methods didn't really have. So the main three are autonomy in sort of a new level. Because LLMs can operate without a direct human intervention, you can have them like prompt themselves multiple times. Um, and they can generate human-like text, engage in conversations, and perform various tasks independently. They can also respond to changes in the environment, and this is done through like prompting, so you can tell it how the environment changes. And then the key thing is the social ability. Because humans communicate in natural language, LLMs are very capable at emulating that. And so it's very easy to understand how an autonomous LLM-based agent uh, might work. Okay. So I want to talk about this paper really quick. This one's very popular. Maybe some of you guys have seen this before. It's called Generative Agents by a team at Stanford and Google. And this was the paper that I think really started the kind of excitement with this area of research. So I'm just going to give a quick overview of it. Basically, what the people did here is they created 25 what they call generative agents that live in a sandbox environment. So this photo right here is a high-level snapshot of the sandbox environment. Um, but this is just like a visualization of the environment. The agents themselves don't actually see this sort of visualized version of their town. They just communicate through natural language. And the way that this paper differentiates just a pure LLM versus like an autonomous human-like agent is um, through their persona. So we see here on the top left, I'm not sure if it's easy to read, but each agent was given a description. So here's an example agent, John Lynn, who is a pharmacy shopkeeper at some pharmacy. He has a wife, May Lynn, who's a college professor, and a son, Eddie Lynn, who is studying music theory. So essentially, what this persona does is when you put it in the prompt to the LLM, you can essentially be like output responses that are representative of this person. So when you have a bunch of different personas, that's how you get a diversity of responses. And so in this paper, what they did is they had using the persona, they would basically create day plans and have these agents act out the day plans in, I believe it was 15-minute intervals. So an example of a day plan for John Lynn is waking up, brushing teeth, taking a shower, cooking breakfast. Then catches up speaking with other agents. So May Lynn and Eddie Lynn are also generative agents. Then he packs and begins his work. So it's sort of akin to how human might be. And I think one of the core contributions of this paper can be seen in the example at the bottom. So in the first dialogue, John is talking to his son. He says, "Good morning, Eddie. Did you sleep well?" Eddie says, "Good morning, Dad. Yeah, I slept great." He says, "That's good. What are you working on today?" Eddie says, "I'm working on a new music composition for my class." And then in a later dialogue, which we see in the bottom right, between May, John's wife, and him, she asks, "Did Eddie already leave for school?" John says, "Yes, he just left. He's working on a music composition for his class." So it's not just putting this persona into an LLM and saying, output believable responses from here. What this paper does is it gives these LLMs in access to an external memory. So here's a quick overview of the architecture of these agents. They can perceive things in the environment, which goes into their memory, and I'll talk a little bit more about that right after this. Then they can reflect and plan, and these reflection and planning modules are just specific prompts for the LLM. So they're just LLM based. And then you convert the plan into some action in the environment. So how the memory stream works is it's basically just a database that's a record of the agent's experiences. So it's just a list of objects, and each object contains a short natural language description, which is basically like an observation by the agent. So here, this is for a different agent named Isabella Rodriguez, but we can see um, that her memory shows that, she's stretching, she's writing in her journal, she's taking a break, she's doing blah, 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 blah. So basically, it's sort of supposed to be akin to like the human memory where we remember things sort of we can remember things in a sequential, episodic fashion. And how they use this memory to improve the behaviors of these agents is they don't just input the whole memory into the prompt for the LLM because, as time goes on, the memory gets large, the LLM context window might not be able to handle it. So they use a retrieval method that they designed on their own, where they factor in recency, importance, and relevance. And once you've retrieved the top like 20 most relevant memories. Um, that's then you input that into the LLM prompt along with the persona, and that's how you get dialogue, like we saw on the previous slide. Okay, so that was just a quick overview of generative agents. Um, but one thing about that paper that's may seem a little bit odd is that there's a massive gap between that text environment that those agents were operating in and the sensory rich world that we as human beings live in. So if we really want to improve these agents to exhibit human-like behavior and actually be helpful to humans, we want to put them in environments where they're forced to have a nuanced understanding of the world. So there's robotics to put agents in the real world, right? You can have a robot with a camera and a microphone and whatnot. But the cost of hardware and physical constraints with robotics makes it not very scalable. So with this paper, viral, grounding virtual intelligence in real life, this was done by some other people in the research lab at NYU. Their core idea is to have a scalable platform where agents can interact with a virtual copy of the real world. And so, as a quick preview, how do they do that? It's through mapping, geospatial, and street view imagery APIs that puts agents in real cities. You can test them out. So I'm just going to play a quick video that's an introduction to this, and then I'll talk a little bit more about it. Let me know if you guys can hear this sound.
We can't hear the sound.
Let me try again. All right. So, Okay. So that went pretty fast. So let me just break this down a little bit. In this paper, they have their own agents with metadata, but they initialize it slightly differently. So each agent has like this 8-bit avatar that we can see on the left. And they have a name, a short bio, as compared to the previous paper with a longer biography, and an intention slash goal they are trying to achieve. So there's different kinds of agents in this platform. The first kind is an earthbound agent, and these agents basically only use geolocation and mapping tools. So they do not have um, vision capabilities or LLM capabilities. These are the simplest kinds of agents in this platform. So here's just like an example agent. His name is Peng. He's 21 and he's in New York City. His bio says he's originally from Chengdu in Sichuan province and is a student at Peking University. And he just arrived for a semester abroad at New York City and is couch surfing until he gets settled. So his task is to, given all these places he needs to visit, he needs to find the shortest path to visit all of them. So this can be done simply by using the Google Maps API. There's not really any um, complex like reasoning behind this. As I said, this is the simplest kind of agent. So we can see on the right here, using the API, he could find the shortest path for biking um, and the shortest path for walking. But what about more complex tasks? Well, LLMs are great at enabling these agents to reason, plan, and use external tools and APIs. So this is where the language-driven agents come in. So the first example here is Aria, who is a graduate student who loves to try new restaurants. And her goal is to pick a lunch spot that Pang might like. So what does Aria do? She uses the Google Maps API to search nearby restaurants. She also uses that API to get public reviews. And then using a large language model, she's able to reason about it and make a final recommendation. So she knows that Peng is originally from Sichuan. So she recommends a spicy Chinese place named Kwa Food Deep Fried Skewers to give him a taste of home. So instead of just, blindly recommending restaurants, um, these agents are able to reason about it. So the next agent example, Vivek, he's a state agent who combines his local knowledge with online tools like Zillow to find the perfect homes for his clients in the city. And Peng wants to hire him to find an apartment in these particular locations with a particular budget, and he has particular things he desires. So Vivek is able to use real estate APIs. So these are not through the Google Maps platform, but other external APIs to find potential places in the desired regions and price ranges. You can then search the proximity of these potential places to the places that Peng cares about. So a gym, a supermarket, and public transit. He also factors in Peng's budget, and then he can provide a final recommendation, which is this middle one right here. So these language-driven agents are sort of a step up from the purely earthbound agents. They don't just have access to the Google Maps API. Again, they can reason on top of it and communicate. So far, though, we've still only talked about agents that are communicating through natural language. And, as I said, what was the motivation for this project was to extend it more into the real world. Um, so this is where the visually grounded agents come into play. So these visually grounded agents are get access to visual information through Google Maps Street View. So I'm sure a lot of you guys are familiar with this, but just to watch a quick video, a demo of it. So basically, you can go on Google Maps, take any place in the world. You can drop a pin where you want, and you have a 360 view, um, where you can essentially look around and move on the street. And this, because you have a 360 view, it's sort of akin to what a human might be seeing when they're walking on the street. And so Google provides this through their API, where basically you can tell it the coordinates and a specific field of view and angle, and it will output a static image. Um, so this is essentially what gives the agents access to the real world. Okay. So here's an example of a visually grounded agent. So this one's not a human, it's a robot who has object detection, localization, and navigational systems. And its task is to um, report the locations of trash bins to the sanitation department. So um, here's an example of this agent in action. Uh, so I'll just Okay, so just want to pause here really quick to highlight key functionality of this, which is that when you're going around detecting places using these AI agents, there's a chance that they encounter the same thing in two different image frames, which makes sense. Like us as humans, if we see something down the street, we can see it from where we are. Then when we walk close to it, we can look to the side and see it right next to us. So for a task like this, where you're counting trash bins, you want to avoid double counting. So they use a feature matching model, which essentially can tell you, okay, this is the same trash bin as before. How this feature matching model works is not super relevant to the agent stuff. So I'll just continue playing the video. Okay. So that is one example of a visually grounded agent. But in that example, the agent doesn't necessarily reason about what they're seeing, right? They have this object detection model that can tell them, okay, this is a trash bin, but anyone can sort of, use the Street View API and just use a, you know, object detection model. It's not really very agenty. So here's another example where you use vision language models or large multimodal models, whatever you want to call it, where you actually have to reason about what you're seeing. So this example is Hero, um, and he is in Hong Kong and he's looking for an authentic lunch spot that is not too spicy. So he's not just going to go and detect all the restaurants on the street. He actually has to reason about whether it would suit his needs. So there's also a video demo showing Hero in action.
أول الطبخ عندنا.
Okay, so as we saw there, he used the reasoning in two situations. First, to decide to go down that particular street that seemed like it might have restaurants. And second, he saw a restaurant, but saw that it didn't really fit his needs. So he moved on to another restaurant. Okay. So in the previous um, generative agents paper, we see these agents like actively communicating with each other in live real time. Um, but sorry, is there a question or um,
Um, yes, so I was just curious
mhm.
on a previous example, let's say as the agent navigates through the map, did you say that those kind of map which have like 360 view are provided by Google by like, through API?
Sorry, could you say that again?
So I was just curious, the
Mhm.
previous example where you're showing an agent navigating through map and
Mhm.
then finding out local places to have food, maybe spicy food, right?
Mhm.
So I'm just now imagining is like there's not like a camera looking around. That's like a map already mapped in a 360 view of the place, and then now the agent can just go through that 360 view instead of just going through camera feeds. That's what I'm just saying. Yeah. How does it work? Maybe if I just mind explaining.
Yeah, yeah. Well, with this particular agent, they don't have access to the map, but how the Google Maps API works is there's like predefined routes to follow. So what it just does is it follows those routes, and add different like coordinate. Basically, what you do is like you keep track of like the the longitude and latitude of the agent. You update that in increments, and then you recall the Street View API to get the images at that new position. So this person's not using like the mapping API that like the first agent was to find the shortest path. I don't know if that answers the question.
Okay. Still not clear. You said so there's like an API where I can get a street view of a long tube, and that to give like a long tube, get a street view. Uh, so my question is, there's those like how do you get those actual like views of the place as agent navigating? Like how do you get them? Maybe if you might
Oh,
mind explaining
oh, like
more
the
slowly.
images, the
Yeah,
images and stuff.
like the streaming of the image maybe and the movement
Yeah,
you're getting
yeah,
the
yeah.
images basically.
So that's provided by the Google Maps API. So if you give it specific coordinates and you give it like an angle, you want it like the angle of it and a specific field of view, it will return an image. So this is like um I showed like the web version of it, like here with this street view. So basically, I think how Google collects this data is they have a car driving around, with like a 360 camera on top. So they have 360 images of the world, and the video shows it like going smoothly in real time. But in actuality, the agent isn't like sort of smoothly doing that. The agent is calling individual images. So the agent isn't processing a video. It's processing images that are called like within specific like intervals of movement. The video part was just for like ease um, of understanding. Does that make more sense, or is it still not
Yeah, yeah. Make it all sense. Yeah,
okay?
makes sense.
Great. Yeah. So as I was saying briefly before, the previously talked about agents, um, or sorry, with generative agents, we see the agents interacting with each other in real time, and we haven't really seen this sort of real time interaction with viral so far. So this is where these collaborative agents come in. So an example here is Ling, who's a traveler, and I'm just gonna focus on her intention in San Francisco, which is to find a store to repair a broken iPhone. So similar to the previous example where you're finding a restaurant, Ling does not have access to a map. Her phone's broken. She can't look at Google Maps to figure out, where to go. So what she needs to do is talk to a local agent who can preview the route um, and then provide walking directions in natural language. And essentially, what Ling has to do is to take these natural language instructions and then follow it in Street View. And if Ling gets lost, she can ask the local agent for assistance. So there's also a video demo quickly to show um, Ling. Uh, Okay. So like under the hood, what's happening here is we're using the LLM to turn like this instruction, like continue straight until you reach the intersection with the Starbucks on your left, into some like actionable code that's like continuing straight is increasing the longitude and latitude in whatever your path is. Then you recall the API for the next set of Street View images. And then you kind of sort of repeat this process. So essentially you're converting this natural language description into ways to like update the API calls.
So I
Yeah,
just to understand um, the agent which who was that agent name? Who doesn't? What's the name? Can you go back and slide?
yeah,
Previously,
Ning, yeah,
so Link was talking to an agent which has access to which calls the API, right?
yeah,
Yeah, and that agent does have link like lifetime, like longitude and latitude. So as she moves, the other agent knows where link is, but it can fetch the actual maybe street view, and now can convert it into proper instruction that maybe now link can follow to move forward. Is that correct?
Yes, yes. So essentially what this other agent does is it goes through the street view path beforehand and, yeah, as you said, converts it into the language for link.
So link must have like location on.
Yeah, yeah. Uh, yeah. Okay. Yeah. And so the final kind of agent in this platform are ones that can interact with humans. So this example is, let's say you're a tourist, you're traveling to some new place. Here we're using New York City as the example, but it's, theoretically anywhere. You can search online for reviews of, what to do, good places to visit. But what if you want sort of a personalized itinerary, personalized plan? So that's what these sort of interactive concierge agents can do. Um, so this agent named Diego, the task is given a user's location, background, and intention for a day, plan a full itinerary balancing their mental, physical state, and budget. So uh, this one, the output of it is a little bit different. Um, Essentially, what these agents do is they just use like the place finding API on Google Maps. They don't necessarily um, navigate it through Street View via like natural language for the previous one. And then they sort of like estimate how your energy, hunger, and whatnot may change as a result of these different events. Yeah, so this one's not really very like agent in the sense of like it's actively performing some action. It's more so just collecting information to output to some human user. Okay. Yeah, so we talked about the different kinds of agents. So I've mentioned a lot of this stuff before, but just to rehash, basically the infrastructure behind um, behind this. So first and foremost is the Google Maps platform, which provides the street view imagery. It provides geolocation, so you can know the coordinates. It provides like pathfinding tools to help you find the shortest path. Then some of the agents used other APIs, such as like a real estate API when he was recommending places to go. And then most of these agents, they're LLM powered agents. So the people in this paper, they tested out two main different kinds of LLMs, GPT-4 and Llama 2. And then they had the localization models. So these are just object detection models that were like trying to like detect the trash bins. So they had various models that they tested out. They also had the feature matching, which tells you if this is like the same thing you looked at as before. And finally, when you're like the sort of reasoning with um, visual stuff is the large multimodal models or vision language models. This is what allows you to look at a restaurant and sort of describe it and then reason about, whether it suits your needs, whether it's spicy food or not. Uh, yeah, okay. So if there's a question.
No question, but because you speak, you've said a lot and you've showed us a lot. And maybe I want to just welcome if there's anyone in an audience we have like a question up to now. Question. I want to know how many so that okay, two. Okay, go on. Yes. Yes.
Sorry, I just wanted to ask. how the computation is the computation about trying to build such kind of agents which manipulate vision, language, how what infrastructure, I mean the terms of infrastructure.
Did you hear that, Ali?
Yeah, just to confirm, he's asking the computational cost of this.
Yeah, like what does it take to actually run those agents? Maybe in terms of
Yeah,
maybe let's say if you're using API, is what you credit, how much, what
yeah,
kind of
yeah,
like numbers around?
yeah. So um, if you are so for the API, I'm not familiar exactly with like the specific cost per like agent query. But you don't actually need any like high quality like computing clusters like GPUs to run this. Because if you just use the like closed source like GPT-4 GPT-4V, um, you don't need to like have your own like GPU setup to run this because you can run the localization models and feature matching models just on a pure CPU. So it's with respect to like computing infrastructure, technically none is necessary. In terms of API costs, sorry, I don't know off the top of my head how much it would cost like per agent.
Correct. Did you? Yeah. Yes, Hasla, you have a question? Everything, of course, okay. Yeah, yes.
So I'm asking you, these agents can be integrated into like applications, right?
Did you hear that?
No, sorry. Do you mind repeating that?
Yeah. So he's asking if this agent can be integrated into something like mobile apps or web apps.
Mhm.
Yeah.
Yeah,
Like
yeah.
integration side.
Sorry, are you saying like the agents are interfacing with mobile apps, or you're like placing these agents in a mobile app for a human to interact with?
Person them in a mobile app or a website for human to interact.
Yeah. Yeah. So you can use the I believe this paper they published like their code. So you can use their code and you can probably integrate it with some mobile app. I can see like using the like concierge agent. You can uh you can put that in an app and people can find personalized travel recommendations. And yeah, I think that's just more on the like app design side as opposed to the like agent stuff. I think you basically just like render um what the output from the agents. I don't know if that answered the question.
Um, Another question? I think we're good. You can proceed.
Okay. Sorry, how much? Okay. So yeah, so I was going to talk a little bit in depth about like agents for task completion. But explaining the previous project took a little bit longer than I expected. So I'm going to try to go through this a little bit quickly. So if anything's not clear, just let me know. So this paper, Web Arena, in the previous examples, we've seen LLM-based agents um, sort of operate like with human-like behavior. But you don't always need like human-like agents. Sometimes you want agents for other practical tasks, such as doing things on the web. So basically, what the this work does is it creates a realistic and reproducible web environment, so you can develop agents that can interact with the web. So what they have is they had four websites. They had an e-commerce platform. They had a social forum platform. They had a collaborative development platform, and a content management systems. They also get in the environment, they also have a map for navigation and searching for information. They have a calculator and they also provide a scratch pad for taking notes. And there also is access to Wikipedia and more specialized knowledge bases. So basically, what the goal of this is to get the agents to do something in the web autonomously. And I'll give examples of tasks later. But just really quickly, how do the agents actually interact with the web? There's three main ways that they do this. The first we see on the far left, which is just a screenshot pixel-based representation of the current web page. Then we have the raw web page HTML DOM tree. So this we can see in the middle. And then on the right, we have the accessibility tree of the web page, where basically the elements are represented as the role, and the text content and properties. So you can think of like the accessibility tree as like a parsed out version of the HTML DOM tree. And then the action space of the agents, they have the following capabilities. So they can click, hover, type, and press keys. They can do tab-related actions such as opening, closing, switching between tabs, and then they can navigate URLs. And basically, with the action space, elements can be selected by on-screen coordinates, just like XY coordinates. And this is for if you're using the like pixel-based representation. And they can also be accessed by like a unique element ID that we get in the HTML. So the goal here was to try to mimic the sort of human experience of navigating. Um, these web pages. And basically, these agents were tasked with a couple of different things. So here are some brief examples. Like first type is like information seeking. So this is where you go onto a website and you get some information. And then site navigation, which is a little bit more of like an open-ended exploration as opposed to like information seeking. Information seeking gets like a specific response. Site navigation sort of just, scrolling for different things. And then content and config. And content and config is the probably the most complicated set of tasks because you actually have to update the state of the environment. Like, for example, if you're posting something, you're updating the website versus if you're just looking for something on the website, you're just like, you're just searching on it. So these are the three main categories. Um, and so basically what they do, this may be a little bit hard to read, but this is the system prompt for their agent. And what they do is they give all the different commands that we mentioned before of clicking, of um, hovering, of all this stuff. And you give it like the user's goal, which is, find information about X. And with that, it will output the specific operation you need to do. And then that operation is executed in the web. So just a quick video demo of what these agents actually look like in action. So here, this first one is searching for earphones on this e-commerce website. And this is not a human operating. That's basically the outputted commands from the LLM converted into action in the web browser. And so this is just another brief example. Okay. So I went through that really quickly. Any questions about this?
I have a question.
Mhm.
Like, does this agent in some sort use some sort of like playwright of Selenium to run this automation?
Sorry, could you say that again?
Does this, like, let's say, it's automatic form submission? Does
Mhm.
the agent in some way use Selenium or playwright underneath? Like, how does
I
it make the web appear?
yeah, I think what it does is I'm not very familiar with this things like the specific code base and how they set it up. But I think what it is basically the LLM outputs the specific command, and then they have some environment that can execute that command in the web. So it's more so like the the like agent part of it is sort of saying which commands to do, but the actual execution of the command, I think, is just like some engineering thing that they set up. Yeah.
Okay, so it's in some sort of ways like, okay, let's say you scrap the page, you give it to an LLM give you a command to run, and then it's go to another like an action, which like another software which take an action maybe now run Selenium or playwright, but it knows now when to fulfill like which field to put information based on LLM response. So in some sort of way, like that's how I think of it. Maybe you have like a scrapper, you have a Selenium automating the browser, and then you have an LLM instructing Selenium what to do. Because I mean, I used to do this Selenium automation, but the way I did it is like I inspect the page and I find field manually. So I'm gonna look manually. Okay, what is the name of this field for the name? I'm gonna copy maybe an ID. I'm gonna copy maybe expert for those fields, and then I'm gonna go manually to my Selenium Python code and automate it. So what I'm imagining maybe with this is go a bit further now. I don't need to look manually on source code or maybe HTML or JavaScript. It can just look at that, give me the structure, and then I can now put Selenium to do the action. Yeah. So that's
Yeah.
just my thought process here.
Yeah. Yeah. That makes sense. Yeah. Um, okay. So, any other questions?
Questions? Yes, yes.
My question is how those visual grounded agents are accurate, the accurate of those visual grounded agents. For example, those means how that visual grounded agent can sense that is being or um, how accurate is it?
Yeah. So he was asking, he's asking about the previous part where we talked about visual redundant agents. He's now asking how accurate are those? Let's say, for example, the agent he maybe took on the street view picture and then it detected there is a bin. Um, so like, okay, now what is the accurate side of it of in terms of when it comes to like visual redundant agent? I think it's the last part, right?
Okay. Yeah. So just to make sure I heard it correctly, you're talking about the like trash bin detecting agents from the previous one. And you're asking how do they know if they're like detecting it correctly? Is
Yeah.
that the question?
So that's one of the example, but it could be to so for so many others like the tasks that agent can do. So
Mhm.
you just ask me, can I rely on this? How accurate are they at the understanding different tasks and executing them? Yeah.
Sorry, it glitched for a second. Sorry, do you mind repeating that?
Okay, so he's asking about the accuracy side of those visual grounded agent.
Hmm.
As an example, is let's say an agent you want an agent to navigate a map and look for you where is the trash bin, right?
Hmm. Yeah.
And then like maybe the agent call Google Map API, call the longitude and longitude, and it find a street view, so trash bin can picture, right?
Yeah.
Uh, so now I think his question is how accurate would you tell like this model will be able to give you trash like a trash bin, something like that? I think it's now,
Oh,
correct me
yeah.
if it's coming now on the model that is urgent to be calling. They say we're going to be using some activity for V to call to know that this is a trash can or not, or you're going to use object detection model. So agent is like, yeah, the way I think of it, like a brain, but you can use tools like the other models, like maybe vision models, other models. For something a trash can, it won't be an agent telling it's a trash can to be now the obfuscation model giving the response. Now agent is using to make a decision. I don't know if I'm correct.
Yeah. That's spot on. Yeah. Yeah. So the accuracy of it is dependent on the accuracy of the object detection models. So if you have a more accurate object detection model, it will be more accurate. If you have a less accurate object detection model, it will be less accurate. Yeah.
All right.
Um,
Yes.
okay. Yeah.
There's another,
So
yeah.
another.
Sorry, Harry. There's another question. Yes.
Uh, could you return to the first screen?
Can you go to the previous screen?
Yeah.
Yes.
Yes. I wanted to just ask one question. You said that it was tested by like 4 websites. So the agent, what it does, it uses the action type. I just wanted to ask, so are those functions like universal? Let's say you have a different website. For example, currently, like you're trying to automate website interaction in Serena, you have to hard code the exact place to like click forward. So I'm trying to ask that were those functions built for each website you have to build for each website, are they custom or universal for any other website you put in
Mm.
the system?
Yeah. So I think it's just supposed to work for their set of websites. Because how they did it is they also didn't, these aren't like live websites. What they took was like frozen snapshots of these websites, and essentially put it in their platform. So the short answer is I don't think these specific actions will necessarily work on all other websites. Though I think if it's like interacting with like the HTML, like for example, clicking on a button tag, I would assume that's probably similar on most websites, though I think these functions were designed specifically for their websites and their environment.
Got it. Any other friends? Yes, yes.
My question is, those models are they implemented like una model ambayo inasimamia hizo model zote au kila moja inaitegemea iko separate? For example, kama kutokea kama kuna mesa au kwa mfano kama kumanage hizo actions. Yeah.
Um, so Ali is asking that is there like a model monitoring all of those like action, like what to action to take, like a supervisor model which is supervising all like the agent actions. This is
Oh,
a question. Like, is there like
is there a
yeah.
model that can do everything?
No, that is supervising everything. Like he's making sure that everything is going according to plan. Yeah. So like a
Um,
supervisor for an agent. Yeah.
I don't think so. I mean, I I think how it works is just like the LLM sort of like the reasoning backbone, and you use like explicit deterministic code to interact with the like object detection models and all the other models. So you don't necessarily need some sort of like obviously the LLM may output the wrong command and do the wrong thing, but there because the code that sort of takes the LLM's output and converts it into an action is like just explicit like code. There's no like sort of AI algorithm to do that. You don't necessarily need like something else supervising.
Right. Any more question? Good. Okay, I think you can proceed.
Okay. So I'm not sure time-wise, how things are looking.
Yeah, I mean,
But
I think you have a few more minutes. We're just waiting for Fully. I think he's coming in the next 10 minutes. I think maybe he'll say 10, um, 10 to 12 minutes.
okay, yeah. So just a final note on this web paper is that GPT-4 achieves a success rate of 14%, whereas humans achieve a success rate of 78%. So there's still a long ways to go with these agents. Okay, so yeah, so just really quickly, I'm gonna talk about the last type of agent that I want to talk about, which is Minecraft. So Minecraft has come to be um, a very useful environment for testing agents because it's interactive. So with the like Street View environment, you don't really update the like what you see in the images. But with Minecraft, you can break a block and that updates the environment. Um, so you can actually directly interact and interface with the environment. And so a lot of people have been exploring how to design architectures, agent architectures, where they can learn how to do tasks in Minecraft. So this paper um, is kind of one of the fundamental papers in this space. And just for context, before I explain it, they're not directly interfacing with the keyboard and mouse like humans do. Sort of similar to that web paper, they're using a JavaScript API that you can write code, and it can perform the actions in Minecraft. So this agent, it just generates codes and that's translated into action. So there's sort of three main key parts to this particular agent, which is first the automatic curriculum. So this curriculum operates under the assumption that LLMs have knowledge, pre-existing knowledge of Minecraft, because they're trained on so much data, they've seen text relating to Minecraft. And basically what this does is it creates increasingly difficult tasks. So the automatic curriculum generates a task for the agent to do, and then the tasks keep on getting increasingly difficult. And there's a couple of parameters to generate the task. So you feed into GPT-4 the agent's current state, like inventory, equipment, and whatnot. And you also tell it the previously completed and failed tasks. And that's how it generates um, the next task. So another important part of this architecture is the skill library. So this is sort of akin to the like episodic memory that we saw with the generative agents paper. So in the skill library, as I said, each skill is represented as some sort of executable code. So the code that we see, for example, in the top right here, this is using I believe it's called Mindflare is the API that if you run this code, it will execute actions in Minecraft. Um, and basically, what you do is you have this code and you essentially store it in a key value database, and you can retrieve it when relevant. So this helps you learn tasks. So if you start with a simplistic task, let's say getting a wooden stick, and then you have a harder task, which is getting a wooden sword, you can refer and query back into the skill library to get that previously learned skill so you don't have to like regenerate the full code each time. But as I'm sure you'd expect, the LLMs do not always generate accurate code on the first try, right? LLMs are prone to hallucination. They sometimes don't follow instructions. So there's environment feedback that helps the language models refine their code. So there's three types of feedback. The first is environment feedback, which is like I cannot make a stick because I need X items, right? The next is an execution error. So for example, the function craft acacia axe, there is none of that item in the game. So this is a language model hallucination. And so um, there will be environment feedback. And the final type of feedback is, I think, a little bit related to one of the questions from before about whether you have something like monitoring to make sure everything works. This final type of feedback has you take the code and you in the inventory and you input it into GPT-4 like a separate GPT agent, and this agent tells you like whether your task will um, will basically fail or not fail. And so just a quick like summary of the algorithm. Um, so basically, you get a new task, and then we see within this like inner for loop, we retrieve all previously relevant skills, and then we generate the code to complete such task. Then we perform the task in the environment, and then we get feedback on whether the task was successful or not. And then based on that feedback, in the next iteration of the for loop, we can rerun it and regenerate the code until we get a successful um, iteration. And then we could store that in the um, skill library and move on to the next task. Um, so yeah, we'll skip over this for now. Um, so yeah, so here's like a video demo of how the agent actually like acts um, in in Minecraft. Yeah. So that was um, completely the agent. And again, it's an LLM generating code, and the code works with the uses the JavaScript library to perform the actions in the environment. Yeah. Any questions on this?
Next question. Yes. Okay. So the room was silent. I don't know if they get it. The, so
Okay.
now, can you explain now? Let's say for this agent in Minecraft, what is an agent doing now in my Minecraft right now? Like I look into the video.
Okay. Okay. So in Minecraft, you have these various tasks of, getting certain items and building certain things. And you have like your inventory of items you collect. And basically what this agent's doing is so there's a JavaScript library where you can write code that will perform the action in Minecraft. So for example, this it might be a little bit hard to read here, but we see in this function it says the sword is bot.inventory.find inventory item, and it tries to find the sword. And if there is a sword, then you equip the sword, meaning you put it in the hand. So the this code is what allows you to act in Minecraft. Um, and so you're not like it's not like a human playing the game. Um, it's just basically this code that gets converted into actions in Minecraft. I don't know if that makes sense. Um, yeah, it seems someone in the Zoom has a question.
So, so far as we know, that for you to play Minecraft, you need to initiate an instance of a server. So, how do you integrate your code base with the server? Do you have do you use Minecraft libraries in JavaScript or Python maybe?
Yeah. So I believe it's called line flare. Um, can you guys see this? It's not the slideshow. So this is a JavaScript library that basically allows you to create a server, create a bot in a server, and essentially like you can visualize what the bot is doing. You can control the bot via this specific code. So yeah, this is a JavaScript library that is publicly.
Got it. Um, and Ali, how like if like from the very beginning of your presentation to here now, if people want to replicate what you did on those agents, or do you have somewhere like resources where you can go and look at and then just focus resources to replicate those agent, let's say those street view? I see a lot of people are interested in that visual generative agent. I think so. Do you have like some sort of repository where we can share? Like maybe
Yes,
somewhere we can
actually,
look at and.
actually, yeah, actually there is. I think this. So this here, it's called LLM Agent Paperlist. This is a repository that organizes a lot of the different papers about this. And the thing about LLM agent papers is that like they're not necessarily always as technical as other deep learning papers that, you know, might be a little bit harder to understand. A lot of these sort of just explain like prompting mechanisms behind these things. And yeah, typically a lot of the papers have like code demos or code implementations. Um, so you could, look through these. Yeah, there's also like survey papers. Um, so here this is a GitHub repository called LLM Agent Paperless. And there also is like survey papers. So these papers, they don't necessarily like propose a specific like new type of agent, but they basically just summarize like previous research. Like for example, this one's like a 50 page or 86 page thing that just summarizes uh the work in the field. In terms of like technical like resources that you need for this, it's basically most of these things you can do without needing, high performance GPUs. It's um, mostly just APIs, so like the OpenAI API, or for example, like the Google, if you want to play with the sort of Google Maps Street View thing, like you can use the Google Maps API. I believe they provide like $300 in free credit for new users. So to get started with this stuff, it's basically just uh, an API. And I guess n nowadays, there's a lot of work with like, quantized language models that you can potentially run on your laptop. So I personally haven't experimented with this, but if you take like Llama, like the 7 billion, 8 billion parameter models, you put them in 4-bit or 8-bit, it's possible to run them on local devices. Uh, yeah,
Got it.
there's
Got it.
So there's a lot online to explore and different tutorials and stuff. Um, Derek, I don't know if you asked your question.
Yes.
Yeah.
Yes. Thank you so much.
I
Yeah,
was
thank you so
asking
much.
on the last module that you showed us about the module about the Minecraft server. Like you said, like there are like there's a list of like prompts, like the AI is like the LLM is given. Like do we do like is the developer is the one that gives the modules like let's say create a wood, create a wooden sword, create like a stone sword, or it's like it's up to the LLM to like decide like it's going to mine wood, it's going to create tables, or like how does that work?
Yeah. So the 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 tasks are generated by an LLM, right? So here we have mining a wood log, um, and stuff. So there is no human intervention needed. And then when you have a more complicated task, the LLM will have to decompose that task into smaller subtasks and retrieve stuff from the skill library. So there is no human thing. You basically just have to, all the humans have to do is design the prompt for the LLM so that it can prompt itself, basically.
You also talked about like the level of like the tasks being done are ordered in the level of like the level of hardness or complexity. Like
Right.
how does the LMM know that this task is more difficult than the other? Is
Mhm.
there like a specific mechanism that you use to tell the AI, the
Yeah.
LMM, that
Um,
this
yeah, yeah. So what it what it's relying on is the assumption that the LLM has been trained on data talking about Minecraft. So it's not necessarily like specific things saying this is harder than that. It's assuming that the LLM already knows that, which granted, like the LLM could be wrong. But yeah.
like it's already pre-trained, so like it
Yes.
knows like fighting a zombie and like creating a wooden sword. Those are two different tasks. Like may let's say they are both given different level of like complexity.
Right. Yes. That's
Okay, thank you.
yeah.
Yeah, so I
Okay.
think,
I mean, no more questions. That's kind of the sum
yeah, I think
of
we're out of
things.
time.
Yeah.
Um, Thank you so much, Ali. This was very, very insightful. Personally, I learned a lot. Okay, go on. So I welcome you to say, just give you 1 minute to give your remark. Yeah.
Yeah. So just want to say thank you. And also special thanks to Frank for, introducing me to this event and, communicating and helping make this talk happen. Also, I'm happy to answer like any further questions you have about this stuff or more like specific resources. So you can just feel free to contact me. My email's right here. Also, you want to ask Frank, and he also has my contact information. So, yeah, thank you all for giving me the opportunity to speak here. It's been really, really fun.
Thank you. Thank you. Yeah, so thank you to Ali. So I think good people are just here. Come on, let me welcome this guy. His name is Sarah Farouk. He's the main sponsor for this event. He's just a young guy.